chordales básicas y algunas de sus clases. Gracias.
Well, the starting point for this presentation are two quite famous classes of graphs that we need to know for all what we continue in this talk. They are chordal graphs and dually chordal graphs. And we also need to know the tree that represent them. As most of you know, chordal graphs are the graphs for which every cycle of length at least 4 has a chord, and they can be characterized as being the graphs that have a clique tree. A clique tree of a graph G is a spanning tree of its clique graph, and for each vertex B of the graph, the family C sub B of cliques containing B induces a subtree of that tree T. For example, this graph G that we have on the screen is a chordal graph. This is its clique graph, and we have a spanning tree for that clique graph. And this tree is a clique tree, and for example, we can see how B induces this subtree of the tree, and I induces this subtree of the tree. And dually chordal graphs can be defined as the clique graphs of chordal graphs. And they also have a tree that characterizes them. That tree is called by us the compatible tree, and it is a spanning tree of the graph such that every clique or every close neighborhood induces a subtree of that tree T. Let's consider again these graphs. G was chordal, then by definition this graph K of G has to be a dually chordal graph, and that means that clique trees of G and compatible trees of K of G have the same set of vertices. So we could try to compare those two classes of trees. Something that we can note is that the clique trees of G are compatible trees of K of G. So we could check, for example, that this clique tree of G is also compatible tree of K of G. To get an idea of that property, let's see that the close neighborhood of these vertices of K of G induce subtrees of that tree, and that would make the tree to be a compatible tree. For example, let's consider C sub 8 and find that the close neighborhood of C8 is a subtree of K of G, of the tree that we have in K of G. That close neighborhood of C8, that is the cliques that intersect C8, are either the cliques that have shape, that is only C8, the cliques that contain H also intersect C8, and the cliques that contain I. All those are subtrees of the tree because the definition of clique tree, and when we combine those trees, they form a larger subtree because they all contain C8, and that ensures that the union of all the subtrees is a connected subgraph, that is a subtree. But the problem is that the converse is not necessarily true. There can be compatible trees of K of G that are not clique trees of G. For example, this other tree is a compatible tree of K of G, where C8, the close neighborhood of C8, now induces this subtree. But however, when we consider D, the cliques of G that contain D are C1, C2, and C6. And the graph that those three cliques induce is not connected. That means that this compatible tree of K of G is not a clique tree of G. Well, the goal of this presentation will be to continue finding relationships between clique trees and compatible trees. This problem is quite recent, the problem of comparing these trees, no more than 2 years, and it was one of the subjects of my doctoral thesis. And well, there were some talks in that time about the subject given by me and Marisa. And for example, one of them was in the previous edition of this workshop. I would like to, well, first of all, in those previous work, we decided to call basic chordal graphs to the chordal graphs such that the compatible trees of K of G and the click trees of G are exactly the same thing. And if we use that name, then one of the main problems that we have is to determine when a given chordal graph is a basic chordal graph. That can be done by using minimal vertex separator. Given a minimal vertex separator of a chordal graph G, we will consider two families of cliques. The family C sub S of the cliques containing S, and the family B sub S of the cliques intersecting every clique set, clique C, that have a non-empty intersection with the separator. For example, when we consider this graph and the minimal vertex separator 2, 5, we can clearly see that the cliques that contain that separator are C2 and C3. Every clique of these graphs intersect the separator. Every clique has either 2 or 5 in them, and the cliques that intersect all other cliques are C2, C3, and C4. We don't have C1 and C6 in that list because C1 and C6 doesn't intersect each other. So B sub S is C2, C3, and C4. We have this theorem that says that the graph is basic chordal if and only if, for every minimal vertex separator of the chordal graph G, B sub S is equal to C sub S. So this graph of the example isn't clearly a basic chordal graph because we have a difference between C sub S and B sub S. But if we have this quite similar graph, we can see that this is really a basic chordal graph. We can verify that with the help of a table where we have all the minimal vertex separator at each row, and for each separator the sets B sub S and C sub S are displayed, and the equality between them is verified. Well, so far we were comparing clique trees and compatible trees, but we can go deeper because chordal graphs have more special types of clique trees. We have the UV, the DB, and RDB clique trees. A UV clique tree is a clique tree such that every C sub B induces a path in T for all the vertices B. The DB clique tree is a clique tree where the edges of T can be directed so that C sub B induces a directed path. And the RDB clique tree is a special case of DB clique tree where there is a root for that tree. And well, we say that the graph is UV, DB, or RDB when it has a UV, DB, or RDB clique tree respectively. For example, let's consider the same graph of the previous slides. We can see that for each vertex, the cliques containing them induce paths that are shown in color here. So we can say that G is a UV graph because it has this UV clique tree. Let's see now if this the UV clique tree can be transformed into a DB clique tree. Let's start by considering the vertex B and the cliques containing B, and we give an arbitrary orientation to the edges of the path induced by the cliques containing that clique. When we now consider D, the cliques containing D are C1, C2, and C6. and to have a directed path induced by them, the previous orientations that we have given forced the orientation of the edge C2, C6. But we have a problem when we consider the cliques containing RH. Because of these two orientations, we can have a directed path for the cliques containing H. So this is not a DB clique tree. With some more work, we could definitely prove that this graph is not a DB graph, and much less it isn't a RDB graph. Well, now let's find out if these classes have dual classes. One can try to find dual classes by using the clique operator, since we know that dually chordal graphs are the image by the clique operator of chordal graphs. But this approach fails because the clique graphs of UV graphs are also all dually chordal graphs, so a new class is not defined. When we consider DB graphs, we do get a new class, and it is suitable to call them dually DB graphs because they can be characterized through a special type of compatible tree that we call the DB compatible tree, which is a directed tree such that the cliques of the graph induce a directed path. And similarly, we can define the dually RDB graphs as the clique graphs of RDB graphs, and they will have the RDB compatible tree, which are the DB compatible trees that are rooted at some vertex. Well, now our focus will be in comparing DB compatible trees and DB clique trees, and comparing RDB clique trees and RDB compatible trees. Well, yes. To start, remember that we have seen that for a chordal graph, the clique trees of that graph were compatible trees of the clique graph. For DB and RDB graph, we will have a similar property. More precisely, every DB or RDB clique graph of G is a DB or RDB compatible tree of K of G. The proof is quite simple. Because DB and RDB graphs are clique-heli, that means that when we consider a clique of K of G, the vertices of that clique are pairwise intersecting cliques of G. So as the graph is clique-heli, there is a common vertex for those cliques, and that will imply that if B is the common vertex, then the clique of K of G is of the form C sub B. And since if we have a DB or RDB clique tree, then that C sub B induces a directed path by definition. Hence, if cliques of K of G induce directed paths, then we can say that DB clique trees and RDB clique trees are also DB and RDB compatible trees. But again, we have that for UV graphs, there are exceptions. We know already that this graph is UV because we had seen that this was a UV clique tree. However, C3, C4, C7, and C5 form a clique of K of G that doesn't induce as a path of the tree. That confirms that it is a good decision not to define a dual class for UV graphs. But however, we have again that the converse is not true. DB compatible trees and RDB compatible trees of K of G not necessarily are DB clique trees or RDB clique trees of G. In this example, this G is a RDB graph, and here for the graph K of G, we define a tree and two orientations, one tree and second tree, and orientations for the edges of those trees. And in the first one, this is a DB compatible tree that is not an RDB compatible tree, and this one is an RDB compatible tree because it is rooted at C4. But these didactic trees are not click trees because this yellow vertex reveals that any click tree of G should have C3 and C4 as an edge because they are just the clicks containing that yellow vertex. So it would be a good idea to define basic DB graphs as the basic chordal graphs that are DB, and such that the DB click trees are exactly the DB compatible trees of K of G, and the basic RDB graphs as the RDB graphs that are basic chordal, and such that the RDB click trees are exactly the RDB compatible trees of K of G. Well, to try to characterize those classes, we need this property that tells us that if G is a basic chordal graph and T is a DB or RDB compatible tree of K of G, then T is also a DB or RDB click tree of G. The idea of the proof is the following. To prove that this really happens, we have to take a vertex B and consider the family C sub B of clicks containing B. And if we consider the members of this family in the graph K of G, they are pairwise adjacent, so there exists a click D of K of G that contains that family. As we know that T is a DB compatible tree, D will induce a didactic path, and on the other side we know that G is basic chordal, so if this T is a compatible tree, then it also has to be a click tree of G. So at least C sub B induces a subtree of T, and this subtree is contained in the didactic path induced by this, and a subtree contained in a didactic path is another didactic path. So we are checking the condition that allows to claim that T is also a DB or RDB click tree of G. The consequence of this property is that basic DB are equal to the intersection of basic chordal graphs and DB graphs, and that basic RDB graphs are equal to the intersection of basic chordal and RDB graphs. One of the inclusions from here to here is implied by the definition of basic DB graphs that I gave before, and the same here. This is contained here, and the contention, the inclusion in the other sense, is because of the property that I have just shown in the previous slide. And most importantly, that means that when we have a basic chordal graph, then there is a correspondence in all levels between the trees. We don't have only a correspondence between the click trees of the graph and the compatible trees of its click graph, but we also have a correspondence between the DB and RDB class trees of both graphs when they exist. Well, and to finish, I would like to briefly show what are the click graphs of basic DB and basic RDB graphs. It will help to remember what are the click graphs of basic chordal graphs. They are all dually chordal graphs, and to obtain, given a dually chordal G, to obtain the graphs in the pre-image of G in the click operator that are basic chordal, we have to take a family F which is separating, and such that every member of F induces a subtree of every compatible tree of G, and F must also cover all the edges of G. When we have a family F like that, the intersection graph will be basic chordal and its click graph will be G. And conversely, every basic chordal graph with those characteristics is of this form. Well, for example, this graph we have seen previously that it wasn't basic chordal. This is its clique graph. And now we could find a basic chordal graph that has this as its clique graph. We can take the cliques and some unit sets because they induced subtrees of every compatible tree by the definition of compatible tree. And when we calculate the intersection graph of this family, we obtain this basic chordal graph, which also have this graph at its clique graph. Well, if we compare this with this, there are some similarities in the shape, but there are some deformations too. Similarly, we will have that the clique graphs of basic DB graphs are all dually DB graphs, and the clique graphs of basic RDB graphs are all dually RDB graphs. And to obtain the basic DB or basic RDB graphs in the pre-image by the clique operator of a certain graph G that is dually DB or RDB, similarly to the property that we saw in the previous slide, we have to take the families that are separating and such that every member of F induces a subtree of every compatible tree and a directed path of every DB compatible tree of G, and again F must cover all the edges of G. In such case, the graph, the basic DB or basic RDB graph that we are looking for is the intersection graph. And well, to obtain such a graph we can still be using cliques and unit sets because they induce directed paths in DB compatible trees and RDB compatible trees by definition. And the last remark is that if we drop the condition that the members of F induces a subtree of every compatible tree, but we leave the condition that every member induces a directed path of every DB compatible tree, then we will have a correspondence between the DB compatible trees of the clique graph and the DB clique trees of the other graph. But this graph, this intersection graph, could be not a basic chordal graph just because we have stopped using this condition. And that's why it is important to define the basic DB graphs as basic DB as a sub. We have to say explicitly that basic DB graphs are a subclass of basic chordal graphs in the definition, because if we omit it and we just say that the class is the class where the DB clique trees are exactly the DB compatible trees of the clique graph, then we will not have a subclass of basic chordal graphs. That's all, and thank you for the attention.